Hello, everyone. Welcome to the first of two narrated PowerPoints all about volcanoes. So I wanted to first say that the title of this first presentation, How Volcanoes Work, comes from Dr. Vic Camp at San Diego State. He's a friend of mine and the volcanologist over there, and he maintains a wonderful website entitled How Volcanoes Work. So thanks to Dr. Camp for letting me use his title here. Well, what is a volcano? There are a couple of different ways of thinking about volcanoes. One way is to imagine that a volcano is essentially the conduit up through which molten rock and solid rock and gases erupt. That is, it's a vent or a fissure at Earth's surface. Maybe a more intuitive definition, though, is to think of the landform produced by the conduit in that second bullet down. That is to say, a volcano would be the mountain or the hill that develops when molten rock and perhaps solid rock and gases reach the Earth's surface. So we're not going to quibble too much about which definition is better or more correct. Already, since you've learned about igneous rocks, you're probably familiar with some of the products of volcanism, namely crystalline rock. And in this case, we're dealing with extrusive igneous rock, including basalt, andesite, and rhyolite, and also pyroclastic rock, that is volcanic rock that's not so much composed of crystalline material, but of tiny or not so tiny rock fragments that are getting blown explosively out of the volcano. Those explosively ejected rock fragments are called pyroclasts. And when they're fine-grained, and those pyroclasts land on the landscape and harden, you get a fine-grained volcanic rock called tuff. And when the pyroclasts are larger, they can also fuse together into a coarser-grained volcanic rock called volcanic breccia. And we also obviously get glass from volcanoes. Remember that volcanic glass is simply material that's cooled too quickly for crystals to form. And glassy materials associated with volcanoes typically include obsidian and also pumice. You can think of pumice as just kind of frothed up or sort of whipped up gas, or glass rather, during gas-charged eruptions. And then in addition to crystalline materials and pyroclastic materials and glass, we also obviously get gases associated with volcanoes and volcanism, principally water vapor. Water vapor is the main gas in all volcanoes, but all volcanoes also exude a variety of other gases in addition to water vapor, including gases like carbon dioxide, sulfur dioxide, sulfuric acid, etc. So no big surprise that most volcanoes occur along plate boundaries. And so in this slide, the red dots represent volcano locations and the black lines represent plate boundaries. And you probably know already from the chapter on plate tectonics that most volcanoes occur at either divergent plate boundaries out in the middle of the ocean, for example, or at convergent plate boundaries, specifically subduction zones. So this entire area sort of around the edges of the Pacific plate is known as the Ring of Fire, and we typically get subduction volcanoes around the subduction zones bordered by the Pacific plate. So you also know, having already been exposed to the material in Chapter 2, that there are some common plate tectonic settings where volcanoes occur. And these include divergent boundaries, where the plates are moving apart. This allows molten rock from Earth's interior to sort of spill out at the Earth's surface where the plates are diverging. And then also we get very explosive volcanoes at subduction zones, where one plate is diving beneath another plate. And inboard from the actual plate boundary, we get a chain of volcanoes parallel to the plate boundary known as a volcanic arc. So The two main plate settings for volcanism include divergent boundaries, specifically out in the ocean for the most part, and also convergent boundaries, specifically subduction zones. Not too much volcanism tends to occur at transform boundaries. The other main setting where we probably get volcanism is at mantle plume locations. And very briefly, you might remember from reading the material so far in the course that a mantle plume in some ways has nothing to do with plate tectonic theory. It's thought to be this sort of shallow vertical conduit of hot material that's rising upward buoyantly, like the hot wax in a lava lamp. And where the mantle plume impacts plate above, if it's able to find conduits to transport liquid rock and other materials to the surface, we sometimes get what's called a hot spot. So a hot spot is just an area of active volcanism atop a mantle plume. And some evidence indicates that some mantle plumes may originate as deep as the core mantle boundary and rise upward as a result. So we can sort of develop two different models, if you will, for explaining almost all volcanism on planet Earth. The plate model, which helps us make sense of volcanism at divergent boundaries and convergent boundaries, and then also the plume model, which helps us make sense of volcanism, specifically if the volcanism isn't occurring at a plate boundary. So there we are. This is just a quick diagram showing possible locations of mantle plumes. I do mention in the reading that unlike plate tectonic theory, which was essentially universally accepted by geoscientists within a few years of its development in the early to late 1960s, geoscientists and researchers are still arguing about mantle plume theory. And although it's fair to say that most geoscientists, a strong majority of geoscientists, think that the plume model is a pretty good one, there continues to be a small and very legitimate and very vocal minority of geoscientists in the world today who don't subscribe to the plume model. And so such contrarians would want to explain the volcanism in places like Hawaii, for example, not in terms of plumes, but in terms of plate-related processes. But for this class, we'll kind of go with what the mainstream science says, and suggest that in fact mantle plumes do occur, at least in some of the locations you can see on the map there. Where do we tend to get volcanoes? Well, we mentioned subduction zones and divergent plate boundaries already, and mantle plumes, of course. It also seems to be the case in some places that where a continent is in the process of breaking apart into two, that lithospheric and crustal extension may ultimately lead to volcanism kind of in the developing gap, as it were. So these areas are sort of like incipient zones of plate divergence. This is where later plate divergence is going to be localized. It's what happened to the Pangaean supercontinent around 200 million years ago. A good place in the world today where we have a continental rift zone is East Africa. The eastern quarter of Africa is tearing away. It's moving eastward with respect to the rest of Africa, and that's what created the Great Rift Valley, where our species evolved. And not surprisingly, we see lots of evidence of volcanism in the Great Rift Valley, including Mount Kilimanjaro. Okay, so what are some features that pretty much all volcanoes have in common? Well, a lot of volcanoes, although not all, have a summit crater where materials are erupting out of the top of the volcano, but it's actually just as likely for materials to erupt out of the sides of the volcano, and we can even get a smaller volcano developed on a larger one. And a lot of times as well, it's not just lava or pyroclastics that get blown out of the volcano, but there are also gas vents as well called fumaroles. This is arguably the most important slide in this entire presentation, so I really encourage you to spend some time going over it in quite a bit of detail. The take-home message on this slide is that we can make sense of how different volcanoes erupt based on 3 different variables, including the gas content of the magma, the silica content of the magma, and even the temperature of the magma. So these 3 things, these 3 variables, which are going to be different from volcano to volcano, are what I refer to as eruptive style controls. And let me walk you through this really quickly so you can kind of understand how it works. Gas content is probably the most obvious, and the simple rule of thumb there is that the more gas dissolved in the magma, the more explosively the volcano is going to erupt. So the way to read this chart, by the way, is from left to right. So if we think about gas content, then if our magma isn't very enriched in gas, it has a low gas content, then we tend to get eruptions that are more effusive, meaning flowy, than explosive. And in the case of magmas without much gas, lava flows are what dominate. In the case of volcanoes that are supercharged with gas, pyroclastics dominate. We tend to get very explosive eruptions as a result of having a lot of gas content in the magma. Well, another variable that's super important when it comes to understanding whether a volcano will erupt explosively or non-explosively is how much silica, that is how much silicon and oxygen, are in the magma. And you know about silica content already from the chapter on igneous rocks. And the way to think of it here is with an analogy that I'm going to use from cooking. Silica is to magma as cornstarch is to sauce in cooking. So if you're making a sauce, for example, and it's a little bit thin and runny, one way to increase the thickness of that sauce is to add cornstarch or flour to it. And what's happening here is by thickening a liquid, its viscosity is increasing. Viscosity just refers to fluid thickness or resistance to flow. And so this applies to magmas as well. If you have a thicker magma, then it's going to have a higher viscosity than a thinner magma. And it turns out that the more silica in the magma, the more viscous the magma is. How does this control the explosivity of the volcano, though? Well, it kind of works like this. If you have a really thick magma with a lot of gas in it, then as that magma rises up into the throat of the volcano and ultimately up towards the Earth's surface, the gases come out of solution, meaning they form bubbles. But if the viscosity of the magma is really high, it means that the magma is so thick that the gas bubbles have trouble escaping. And if more and more bubbles are coming out of solution and forming in the magma, but being prevented from escaping, then gas pressures are going to skyrocket until, boom, the magma blows up. That's when you get a highly explosive pyroclastic eruption. So I want to emphasize again that assuming that gas is present to begin with, it's high viscosity, thick magmas that tend to be more explosive than lower viscosity, thinner magmas. So this relates to magma composition. If we think about mafic magmas of the sort that we have on the Big Island of Hawaii, those magmas are relatively low in silica, and so they're not very viscous. They're thin and runny, and so when the magma erupts, the gases can escape easily, and you don't get a very explosive eruption somewhere like Hawaii. Instead, you get more effusive eruptions where lava flows are able just to kind of trickle down the side of the volcano. In other situations, though, for example, if we have maybe an intermediate or even a felsic magma developed at a subduction zone, for example, then assuming the magma is gas charged to begin with, it's the high viscosity of the magma, the thickness, that prevents the gases from escaping, and that ultimately leads to really explosive eruptions dominated by pyroclastics as opposed to a lot of lava. Okay, and then finally, in addition to gas content and silica content, magma temperature also plays a role in determining how explosively the volcano will erupt. And here again, we can use a cooking analogy. Pancake syrup in the refrigerator has a high viscosity, but a low temperature. If you pull that pancake syrup out of the refrigerator and warm it up on the stove, then as the temperature of the pancake syrup goes up, as the temperature increases, the pancake syrup will become thinner and more runny. In other words, as the temperature rises, viscosity decreases. As the temperature decreases, viscosity increases. And so, somewhat counterintuitively perhaps, it turns out that low temperature eruptions tend to be more explosive as a rule than higher temperature eruptions, because if the magma temperature is lower, it means the viscosity is higher. And that high viscosity, as we talked about, prevents gases from escaping, and that allows magma pressures to build up and build up and build up until boom, everything explodes in more of a pyroclastic eruption. Okay, so just a quick review. There are 3 eruptive style controls that you want to be familiar with, and these include magma gas content, magma silica content, and magma temperature. In general, magmas that are more gas enriched tend to erupt more explosively. In general, magmas that are more silica rich tend to erupt explosively. And in general, magmas that are cooler tend to erupt more explosively. This is also a really important slide. You want to be familiar with the 3 main types of volcanoes shown on this slide, including shield volcanoes, scoria cones, also known as cinder cones, and stratovolcanoes. Shield volcanoes, as we'll see in a minute, are by far the largest, but they tend to have relatively gentle side slopes, as you can see here. In fact, that's how shield volcanoes get their name, because the volcano itself sort of looks like an inverted warrior's shield on the ground. So shield volcanoes are the biggest, but they have the gentlest side slopes. At the other end of the spectrum, we have scoria cones, also known as cinder cones, that are quite small as far as most other volcanoes go. And I like to describe scoria cones as locally explosive. That means that when they erupt, they do tend to erupt pyroclastic material, but the eruptions don't tend to be large and catastrophic. And then finally, intermediate in size between shield volcanoes and cinder cones, we have stratovolcanoes. And stratovolcanoes tend to be composed of alternating layers of lava and pyroclastic material. And stratovolcanoes are much bigger than scoria cones, but they tend to be, as a rule, much smaller than shield volcanoes. Here's a good comparison of volcano sizes. Again, shield volcanoes are by far the largest, cinder cones by far the smallest, and then stratovolcanoes, also known as composite cones, by the way, are intermediate in size between shield volcanoes and cinder cones. Very quickly, just a few other types of volcanic landforms. One type shown here is known as a lava dome. And this is a result of gas-poor, highly viscous lava. So let's imagine a volcano like Mount St. Helens, and after it's already erupted, the magma, in a sense, has gotten rid of its excess gas. And the highly viscous, highly felsic lava in the throat of the volcano may continue to erupt, sometimes for many years after the main eruption. And all that's happening here is this material is just sort of pushing upward like a piston or toothpaste out of a tube, and it tends to pile up into relatively steep-sided piles. As a rule, lava domes at least for most of their lifetime, don't tend to be overly explosive, because by the time the dome is forming, the magma has already gotten rid of most of its gas. And if you click on this link down here, you can actually see a time-lapsed video of the growth of the Mount St. Helens lava dome. But the main image here is just an example of what an actual lava dome looks like in or on a volcano in Indonesia. Another interesting type of volcanic landform is known as a caldera. And in some ways, a caldera is the opposite of what we normally think of as a volcano. It's more of a volcanic collapse feature than a hill or a mountain. So let's imagine in step one, you can see on the screen, we have a relatively shallow magma chamber, probably pretty felsic in composition. And imagine that during the early stages of the caldera forming eruption, the magma chamber partially empties. As it empties, however, it can no longer support the weight of the volcano itself. And so what happens is the volcanic material above the magma chamber simply collapses into the magma chamber itself. Essentially what happens during caldera formation is the roof of the magma chamber collapses into the magma chamber itself. So there's roof collapse, and now we kind of have this big volcanic sinkhole. That's the caldera. And very often, when the caldera forms, it pushes out a lot of the remaining magma to create really, really massive pyroclastic eruptions. Here's an example of Crater Lake in Oregon. That's actually a caldera. And then this small volcano kind of inside the caldera is known as Wizard Island. And it's a little cinder or scoria cone that's been built up after the last caldera forming eruption in this case. So here's a shield volcano. Again, shield volcanoes are absolutely massive, but they have really, really gentle slopes. This is ultimately a reflection of both the temperature and the viscosity of the lava. Shield volcanoes are built literally one lava flow at a time. And after many, many lava flows, the volcanic edifice created is the size of a mountain. And at that point, we start calling that mountain a shield volcano. Mafic magmas tend to be really hot. And so because of that, the viscosity of the lava is low. And so you tend to get low viscosity runny lavas that just sort of pour down the flanks of the volcano. Also, mafic magma tends to be low in silica, and so for that reason as well, mafic magmas tend to have a low viscosity, so the gases can easily escape and lava flows can travel far. Bottom line, shield volcanoes are not very explosive. Here are just a few examples of a shield volcano. In the upper left corner of the slide, this is actually a picture I took of the Mauna Loa volcano at sunset many years ago when I was on the Big Island of Hawaii. And you can see here that just like all shield volcanoes, the side slopes of the Mauna Loa volcano are not very steep. And by the way, shield volcanoes are not just confined to Earth. Olympus Mons is a large shield volcano on planet Mars. It's about the size of the state of Arizona, and it's 3 times the height of Mount Everest. There's also a shield volcano on Venus called Sif Mons. This is a smaller shield volcano in Iceland. Some of the Galapagos Islands are also shield volcanoes. This is really a slide meant to convey how volcanic eruptions can be tracked and even predicted in some cases. This is the Kilauea shield volcano on the Big Island of Hawaii. It's probably fair to say that the Kilauea volcano is the most monitored volcano on the planet. So beneath the summit caldera, there's a large and active magma chamber that sort of sends out magma stringers in various directions. And right now, the main source of activity on the Kilauea shield volcano is actually not occurring at the summit. It's occurring far away from the summit, a number of miles away from the summit, near sea level. And this is known as the Pu'u'o'o vent. It's primarily a cinder cone. And geoscientists in Hawaii can actually track impending eruptions by looking at the earthquake signature of this area. When magma moves into this horizontal conduit and starts moving towards Pu'u'o'o, that creates earthquakes. And it's literally possible to track the movement of earthquakes to be able to actually predict eruptions in the Pu'u'o'o vent. But in addition to earthquakes, geoscientists install what are essentially fancy levels on the flanks of this volcano. They're called tilt meters. And typically in the days and weeks and months leading up to a major eruption, the volcano itself will inflate. It'll expand a little bit like a balloon when you fill it with air, and that causes the tilt meters to sort of tilt a little bit. And also GPS. If you imagine, say, a GPS sensor here on one side of the caldera and over here on the other side of the caldera, when the volcano inflates, both GPS sensors will move upward and outward relative to the other. And so that's yet another way that volcanic eruptions can actually be tracked and even predicted on the Big Island of Hawaii. And then finally, very often, what will cause a new eruption is a fresh influx of magma from below. And with that influx of new magma from below, new gases are added to the magma that ultimately escape from the magma even before the eruption occurs. And so by monitoring the gases coming out of volcanoes, volcanologists will look for short-term changes in the chemistry of the gases. That too can signal that an eruption is impending. Quick example of the Pu'u'o'o vent. It's mostly a cinder cone, mostly composed of cinders, volcanic fragments. But if those cinders are still liquid, they wouldn't really be cinders if they're still liquid. But if the magma, as it erupts in the air and then it lands back on the ground when it's still liquid, it forms a sort of pancake-ish material called spatter. And so some of the material you're looking at here in the Pu'u'o'o vent is cinder, meaning solidified, cooled pyroclastic fragments building up around the vent. And some of the other material is spatter, meaning volcanic rock that's hardened after it landed. I encourage you to, when you're looking at this PowerPoint in the non-narrated format, if you click on each one of these photos, you can see interesting examples of different basaltic lava flow types, including Pahoehoe lava, which is kind of smooth and ropey, A'a lava, which forms irregular jagged fragments. And if lava erupts underwater, it forms these sort of bulbous shapes that are known as lava pillows. And in this case, you can get something called pillow lava. It's an indicator that the eruption was happening underwater. Some more examples of Pahoehoe lava flows. Typically, Pahoehoe flows tend to consist of really, really hot basaltic lava of relatively low viscosity. And then here's some examples of A'a flows. In some cases, when a lava flow first erupts, a basaltic lava flow, that is a lava flow of mafic composition, when it first oozes out of the volcano, it's a Pahoehoe flow. And then as that lava flow travels down the flank of the volcano, it cools and it begins to solidify and crystallize. It also loses some of its gas. And even though it may continue to flow, it's partially solid at this point, and the solid part of the flow is continually breaking up into fragments that are actually called clinkers, because as the fragments sort of fall down the face of the advancing lava flow, they make a sort of clinking sound. So this is another main type of basaltic lava flow called A'a. and some examples of pillow lavas. This is a photograph that I took on one of the trips that I lead to Iceland. We came across a really nice exposure one day of pillow lava, and so someone is sort of yucking it up for the camera, pretending that the rock there is a pillow, and not too far off the mark because it's pillow lava.